This is Chapter 4, Part 6. Okay, we are almost done with Chapter 4. We've talked about that least squared regression line. We've talked about using both the least squared regression line and the mean of the y values in order to make predictions. The last thing we want to talk about is being able to interpret the slope and y-intercept of that least squared regression line. And of course, this is only when the least squared regression line is useful, when our R value is large enough, when our linear correlation is strong enough. So first of all, if we want to draw this least squared regression line on our scatter diagram, we can easily do that. In fact, it's probably already done. You just need to hit graph again. The main thing we want to make sure we do is to let that regression equation be stored as y1. So if you haven't already done that, let's take a look at how we can do that really quick. All right, so like I said, more or less, we've already got this set up. You may just have to hit the graph button, and you'll see this already if you've been following along with your calculator thus far. So the main thing we have to make sure we do if we want to see that equation show up in our graph, we've got to make sure we do that store reg EQ, store the regression equation as y1, or into y1. And again, to get to that y1, you're going to hit the vars button. You're going to go over to y-vars, and then you're going to hit enter twice. And that'll put that y1 in there. Then you can go and calculate. It'll give you all of the information for the linear regression, but if you actually want to see the line with the data, then you can just hit zoom 9 again in case you have looked at a different graph. Or if you just looked at the scatter plot before, then you should just be able to hit graph again. And when you do, the line will be right in place. And so we can see how closely our data follows that line. All right, and then the last two things we want to do is to be able to identify and interpret the basically the A and the B, the slope and the y-intercept for our least squared regression line. So what is the slope and how do we interpret it? Well, luckily, it looks just like any other equation that we would have seen. So we're able to use hopefully that information that we have from before this class, to know that, y equals mx plus b. That's that basic. And so knowing that, there we go. Knowing that equation, that y equals mx plus b, same thing. Yes, our calculator calls it a and b instead of m and b, but that number in front of the x is still our slope. So the slope is 0.012. Now, slopes have units. I remember we said that the linear correlation coefficient, does not have a unit. That R value is unitless. But slope has a unit. It's a rate. That's what a slope is. It's a rate of change. And our units are always, think about what slope is. So let's go back to, it's the rise over the run. It's the difference in the y's over the x's. And so that's going to be, the units are going to be the units of the y. Remember that was minutes. And then the units, divided by the units of the x's per foot. Now, what does that mean? That's kind of weird. That seems strange. Minutes per foot instead of feet per minute. But we're not talking about the speed of drilling a certain distance. We're talking about how long it takes based on a starting distance. We got to really understand that problem that we're talking about. And so what this slope ends up being, and I'm going to switch over to a new a new page so we can write it out. But it's just talking about that the slope is 0.012 minutes per foot. Minutes per foot that they started. So let's interpret that out a little bit better in a full sentence. All right, so once again, our slope was 0.012. We were rounding to 3 decimal places. We could have taken it out further, but I think this is fine. And what that means is that for each additional foot of depth we start drilling, so remember we were talking about based on how far down we are when we start, how long will it take to drill 5 feet. So for each additional foot of depth that we start drilling, the time to drill 5 feet increases by 0.012 minutes. Oops. On average. Now, I'm not good with decimal portions of minutes, so I'm curious, it increases by how much? So this isn't part of the question. This is just, for me, I would rather know what this is in some unit that makes sense to me, in which case, if it's part of a minute, then I would like to know how many seconds that is. So I'm going to multiply 0.012 times 60, and it's not even a whole second. So 0.012 times 60 seconds. Well, let's see. Let me just go ahead and do the entire conversion correctly. So that's minutes. And then I know that there are 60 seconds in 1 minute. So this is the conversion I'm doing. So my minutes cancel. I want seconds, so that's all I need. And so when I do this, I get 0.72 of a second. So again, not even a whole second for each foot that so if we're at 130 feet, if we go to 131 feet, we would expect it to be an additional, almost 1 second. That's what this slope actually means. All right, well, what about the y-intercept? Well, we can always identify the y-intercept, but we can't always interpret it. Sometimes it's not a reasonable value, and so we're going to talk about that. Let me go ahead and identify it here. So again, we had y hat equals 0.012x plus 5.527. That was our least squared regression line. So the y-intercept is the number by itself, the constant, and that is 5.527. And it is a y value, the y-intercept, so that's minutes. All right, so we need to figure out if it's reasonable to interpret, and then if it is, what is that interpretation? We're going to need some more room for that. Okay, so before we can interpret this y-intercept, we have to ask ourselves 2 questions. And these are both very important because this value may or may not make sense. And so the first question we want to ask is whether or not, so is 0 a reasonable value for the explanatory variable? And sometimes it's not. So if I'm talking about height and weight, the height of a person versus their weight, then putting in 0 for someone's height is not going to be reasonable. Because someone can't be 0 inches high. Even babies born prematurely and teeny tiny. My niece, when she was born, was literally smaller than my mom's hand from fingertip to the base of her palm. So that's small, but it's still more than 0. And so that 0 is not a reasonable amount for height. So is 0 a reasonable value for the explanatory variable? The next question we need to ask is, do any observations near x equals 0 exist in the data set? Now, here's the problem. This one's a little more relative to what your possible values could be. So in this case, is 0 a reasonable value for the explanatory variable? Well, yes. I could have 0 feet, a drilling depth of 0 feet to start with. So, yes, that part's fine. That would be just starting at the surface of the earth. Do any observations near x equals 0 exist in the data set? Well, this is where it comes in like, maybe, maybe not. In this case, I think we can say that that smallest observation in our data set where we had x equals 35 is reasonably close to 0. So the interpretation of our y-intercept is reasonable. So we're going to go ahead and say yes to this one as well. Now, to actually interpret, so our interpretation would be that the time to drill five feet when beginning at the surface, or I'll say the Earth's surface. Sounds a little better. I don't know why, but it just does. Is 5.527 minutes. Oops. There we go. And that's 5.5 would be 5.5, so 5 minutes, 30 seconds. This is a little bit more than 5.5 minutes. So when they're first starting, and that would be fine. That's a reasonable interpretation. Now, there's one thing I want to caution you about, and that is trying to predict values outside of our data set. So I can interpret the y-intercept like this, but I wouldn't want to try and predict values beyond that data set from 35 to 190 feet. So I wouldn't want to try and predict how long would it take once we start at a depth of 250 feet. Technically, I really wouldn't even want to do it for 200 feet. But I can't predict outside the scope of the model. That's one of those things that we just can't be sure that linear relationship continues to exist beyond what we have data for. That would be like trying to predict, continue to predict for coronavirus right now. They're doing that, and you may see some of those graphs that, they've got these starting off, and they know that it's like this, and then, we're up here, and then you might start seeing these dots. And then, but they also kind of have dots going out this way. And then they might have dots and they might have it going steeper because they don't know. That's what they're doing. They can't predict past what they know, but they can try and make some estimations. And so we do not want to try and make predictions beyond our data set.